A2 Maths, Normal Distribution, Hypothesis Testing. Okay, so the battery life on a phone can be modelled using a normal distribution. So we just looked at normal distribution, so the battery life on your phone can be modelled using a normal distribution. The phone manufacturers say that the battery life on their phones has 1080 minutes with average usage. They also state in there that the phone battery has a standard deviation of 30 minutes. So we've run some tests on this. We check it. So we take a sample of the battery life taken over the last 8 days, and the following times have been recorded. Okay, so there's the different amounts of time before the phone battery ran out. What is the mean of this sample? So there you go, really quickly, grab your calculators, just work that out, see what you get for your mean. Okay, pause if you need to. Right, so hopefully you added it all together and divided by 8, in which case you got 1066. Question is this: would you doubt the manufacturer's claim? So just pause it, have a think, yes or no, and reasons why. Okay, so let's see what you thought. You could have said, well, yes, I would doubt it because 1066 is definitely lower than what the manufacturer stated. It's definitely lower, isn't it? So I would write that. I'd say the sample mean, the mean of this little sample set we got here, is definitely below what the manufacturer said. But how far below is it? Well, it's only within one standard deviation. In fact, it's quite a lot higher than one standard deviation below the mean. It's not massively below what the company are actually saying. So although it is below, it's not really that far below, and it's certainly still within one standard deviation, as you'd expect about 2/3 of the phones to be. So what we're going to do to actually check whether it is true and whether we should doubt the claim, that's where we're going to have a look at running a hypothesis test. We can run a hypothesis test to check whether, after we take this sample of 8, we could doubt the manufacturer's statement and therefore complain to the manufacturer. So let's just have a recap of what a hypothesis test is and how to run a hypothesis test. I know you did this with binomial distribution, but we can also now do it with normal distribution. And there's a lot of similarities with how to run a hypothesis test. There's also some differences because normal distribution is what's called a continuous distribution as opposed to binomial being discrete. But we'll have a look. So a statistical hypothesis test is used to check an assumption about the population mean of a normal distribution. So like you just saw, we're checking the population mean of the battery life on that phone. The null hypothesis refers to the population mean that's being tested. So your H0 is P equals mu. Okay, so we're setting our null hypothesis to what is stated. So in the previous example, it was the 1080 minutes that was our average that we're checking. An alternative hypothesis refers to the region of values that will either accept or reject the null hypothesis. And the same as before, it could be greater than the mean, it could be less than the mean, or it could be that you're just not happy with what the mean is, and it could be either greater or less than. Okay, you just don't think it's right. So in that previous case, you could be thinking, my phone runs out a lot earlier than 1080, so therefore you think it's below the mean. You could be thinking, actually, this company seems to underestimate because my phone seems to last forever, so therefore you might be greater than the mean. And you might be thinking, it just doesn't seem right. Okay, 1080 doesn't seem right. It seems sometimes lasts more, sometimes lasts less. I won't need to check it. So the 3 possible outcomes you can get on a hypothesis test then is if it's too high, so you think it's too high, then your H0 is going to be less than mu because you think the null hypothesis is too high. Null hypothesis is too low, in which case P is greater than mu, or you might just think it doesn't seem right, something's wrong with it, so therefore it's just not equal to what the company are saying, or you're not equal to your null hypothesis. So you need to state which one of those is the most appropriate once you've got a scenario. This bit here is always the same, of course. You always have something equals this statement. These two here are what's called a one-tailed test. And again, we saw that with the binomial, so because you've only got one side or one side there, whereas this one is a two-tailed test because it could be on the lower side or on the higher side. It's just not the one in the middle. Okay, and it's important to make sure you're aware of one-tailed and two-tailed tests because they can affect the significance level. Right, to determine if you accept or reject a null hypothesis, you need to have a test statistic. So our test statistic for this does look very complicated, but it is a formula you're given, so you just need to learn how to put the parts into it. So when you calculated the sample population, the test statistic is used in a hypothesis test for the mean of a normal distribution. And it looks like that. Right, so let's just get our head around what this is talking about. So we know about Z, because Z is the standardized part of the normal distribution curve with a mean of 0 and a standard deviation of 1. We know what X bar is. X bar is our mean sample size. So in that previous example with the phones, that was the mean we got that you guys calculated on your calculators. I think it was 1060 something. This is the mean that the company is saying. So that's the 1080. So that's the difference between what the company is saying and what you've calculated from your sample. This number here, sigma, is the standard deviation. So that was the 30 minutes just there. That's the 30. And this is the only bit that seems a bit new. This bit here, the end value, is the sample size. Okay, so let's run through that. The mu is the mean of the population, 1080. Sigma is the standard deviation of the population, so that's the 30 minutes. X bar is the mean of your sample. And the final bit is n is the sample size. So the bigger your sample size, the better. The better your approximation. The bigger your sample size, the more you're dividing by. Right, so the value of the test statistic is the number of standard deviations the sample mean is from the population mean. That's what you're trying to check there, because that Z value tells you how far away you are from the mean. So when you work this value out, and you might have something like, let's say, 1.2, that means you're 1.2 standard deviations from the mean. It's not as simple as just checking that previous one because we didn't consider sample size when we looked at it earlier on. And we said there's only one standard deviation. Okay, so let's run the hypothesis. Let's have a look and just make sure we understand how to go through the stages of the hypothesis test. So the p-value is calculated using the test statistic. And we notice that the test statistics we use is always Z is distributed normally with 0, 1. So it is the standardized normal distribution that we saw in the previous lessons. The p-value equals the probability that our standard curve is lower than some Z value. Okay, and that's if the test statistic is negative. So if our test statistic comes out to be negative, we know from our normal distribution curve that we've seen already. So let me just quickly show you what I mean. So this is our normal distribution curve. Oh, it's a very rubbish normal distribution curve. But because that's 0 in the middle, right, which is where that bit comes from, what it's saying is if it comes out to be less than something, then you're talking about it being in this region. So Z has got to be on the negative side. Whereas if it's greater than Z, it means it has to be on this side because it's this sort of area. So therefore the test is positive. Now we'll make more sense when we start looking at an example of that. Okay, right. Let's get rid of that. There we go. Right. So if the p-value is then compared to the significance level, so once we get our Z p-value out, we can compare it to our significance level and determine whether to accept or reject the null hypothesis. So it sounds quite technical. So let's look through an example of that and it'll make more sense. The significance level is always given at the start of the test. Unless they give you more information, you have to go back and calculate that. And it's denoted by alpha. So that's almost the same as binomial. So p-value is less than significance, then we reject the null hypothesis. Okay, so if the p-value is less than significance, then we can reject the null hypothesis. But if the p-value is greater than significance level, we accept the null hypothesis. And we would say there is significant evidence to suggest that we can reject the null hypothesis, significant evidence to suggest that the null hypothesis is correct. Okay, and that's what it's saying here. The higher the significance level, the more likely you will reject the null hypothesis, but the more likely you would have made an error. And also, the lower the significance, the more likely you will accept the null hypothesis. Okay, but again, that null hypothesis might be wrong, so you don't want the significance level to be too low. You've got to find that happy medium. The significance levels we talked about before are always 10%, 5%, 1%. They're the standard ones. And if you're doing a two-tailed test, so in other words, it's a not equals to, then what we need to remember is that our p-value is half of the significance level. So instead of looking, so if we got asked to do a 5% significance, we need to remember that we've got 2.5 on this side of the curve and 2.5 on that side of the curve, because there's a total of 5 altogether. Okay, so grab your notebooks, make sure you've got these steps written down. The first thing you need to do with any hypothesis test is just define the population parameter. So that's basically writing out the distribution. So in our case, we're looking at the mu being the mean battery life of the phone. So that is what our mean represents, the mean battery life of the phone. So make it nice and clear what it actually is. You've got the population parameter. State the null and the alternative hypothesis and the significance level. So that's just given to you in the question. So just write it down to get to make sure you've got it written down somewhere. We've got the null and the alternative hypothesis. So in our case, the null was H is a mean of 1080. Now we didn't think that was right. We thought it was too high. So our alternative is that the mean is less than 1080. The significance level we're going to work with is 5%, which we can read off the question. That will hopefully be given to you. But again, just be wary if it's a two-tailed test. Right, state the population distribution and then calculate the sample mean of the test statistic. So state the population distribution, that is this here. X is distributed normally with a mean of 1080 and a variance of 30 squared. 30 is the standard deviation. Our sample that we calculated, our X sample, was 1066. Okay, that was from our size 8 sample. So now what we can do is we can work out test statistic. It's going to be 1066 from there, it's 1080 from the mean, it's 30 as a standard deviation, and our sample size was 8. So if we put that in our calculator, out comes minus 1.32. So it's definitely below the mean. Notice it looks like it's over one standard deviation, or it is over one standard deviation below the mean, and that's because we didn't consider sample size in our first example. Okay, so although 1066 is definitely less than 30 minutes from 1080, we didn't consider the sample size when we looked at this. Okay, but now we are. So we got minus 1.32. Calculate the p-value using the test statistic. So we know what's the probability that z is going to be less than 1.32. What is the actual chance of that happening? So what we can do is we can put that in a calculator and we get 0.093. So 0.093 is the probability that we get less than minus 1.32. We can compare that probability value with the significance and then write as a conclusion. So at the moment, that is roughly about 9%. Okay, the chance of that happening is about 9% of the cases. Now 0.93 is greater than 0.95, our significance level. So therefore, there is a significant evidence to suggest the battery life is 1088. Okay, so we kept the null hypothesis in that case. We accepted with significant evidence the null hypothesis. Okay, so let's have a look at another example. Make sure we can follow through those steps. So It does say notebook, so you can get it down. You can summarize a little bit if you want to. You can't cut out too much though. So bottles of juice contain 1,000 millilitres. That's what the company say on the side of their bottle. After the introduction of a new bottling method. So the company are actually doing something different. The factory's doing something different. And they think after this new machine's been put in, that the mean volume of the juice has changed. So they don't think it's 1,000 anymore. So they need to do some adjusting, but they need to check it first of all. The standard deviation of 5 remains the same, so they're still happy with the standard deviation of 5, and the random sample of 12 bottles was taken and the volumes are calculated. So there we go. Investigate a 5% level of significance whether the mean volume of the juice differs from 1,000 millilitres. Okay, so the first thing we need to do is define the population parameter. So the population parameter is going to be the mu, the mean volume of the juice in a bottle. State the null and the alternative hypothesis and the significance level. So we pick that out of the question. So we've got 1,000 is our mean. The alternative thinks it's just changed, so therefore it's not equal to 1,000 is our null hypothesis. We also just write down, there we go, 5% level of significance, but we're aware that because it's not equal to, that's going to go to 2.5. Right? So we just keep that awareness in our head that we're going to compare 2.5, not 5. State the population distribution and then calculate the sample mean and the test statistic. So we've got 1,005 squared because it's a variance, so it's 5 squared. And the mean, if you calculate that, add all this together, divide by 12, is 1,003. So not much difference there, but is it enough to doubt whether it stayed the same? So the test statistic is x bar minus mu, so that's going to be the difference between those two, which of course is just 3, divided by the standard deviation, which is 5, from there it's 5, over the square root of 12. So there we go, put those numbers in, work out your answer, 4 significant figures, 2.078. That is our test statistic that we need to compare. So in this case, 2.078, what is the probability of getting 2.078? That's what we want to do. Notice because it's greater than, right, 0 on this side of the normal distribution curve, then what's going to happen is we are looking at it being greater than z. So what's the probability that it's greater than 2.078? If 2.78 was just a norm, it could have been worse. So what's the probability of getting that or worse? And you get your calculator, we could do 1 minus the probability of it being less than equals 0.0189. Now we've got 0.0189, we can check whether that's enough to see whether there's a change or not. So we compare the p-value and the significance level, and we can write our conclusion. So in this case, 0.0189 is less than 0.025. So there's sufficient evidence to suggest that the mean volume of juice differs from 1,000. It was smaller than what we expected, so therefore we doubt the claim by the company, or in this case, we doubt whether the machine has managed to keep it 1,000 millilitres. Okay, we're going to look at a slight alternative to running hypothesis tests. It's an alternative method. Some of you might prefer it, some of you won't. So in that case, you can stick with what you had previously. It is up to you. So let's have a quick look through this alternative way of doing it. You still need to understand about critical regions, things like that anyway. So the test statistics that lie in what we call our critical region, just here, okay, are the ones where you would reject the null hypothesis. So it's far enough away from the mean so that you would reject that null hypothesis. So when we come to working out what this percentage is, it's to do with the significance level. So for example, if I had a 10% significance level, that would be 10% of the graph. Okay, I could also say that the probability of it being below mu, below the mean, would be the critical region. Okay, now the value that changes from the critical region to what we call the acceptance region is that critical value just there. Okay, that critical value can be calculated and given a z-score. So you could get your calculators now. If this was and it is, you can see it. 1, 2, 3, 1, minus 1, 2, 3. It is just a z-graph. You could calculate what probability you'd have to be to have less than or equal to 10. So you can calculate that critical value, that cutoff mark. Everything on this side is what's called the acceptance region. Now, none of those bits are new, but they are bits you need to understand. Even if you don't use this method to solve your hypothesis testing, the examiner will still expect you to understand terminology like critical region, critical value, acceptance region. Okay, so a 10% level that is not equal to mu, so a two-tailed test, what difference would that make? Well, you would end up with 2 critical values and 2 critical regions, because it might be that it's greater than it might be that it's less than it. We just saw an example there with the different machine, and that was a two-tailed test, but we noticed as we collected our sample, it was definitely going to be on this side rather than this side, which is why we looked at greater than a certain value. But in this case, if it's 10%, you would have to split both sides equally to 5%. So, given a 10% significance level, an alternative hypothesis is the probability it's less than mean. What is the z-score? Equal when it's equal to 0.1. So you grab your calculators, have a go at that, just pause, make sure you've got enough time to practice it, see what you get. Okay, so you used your calculators, you worked out this value just here, and it comes out to be minus 1.28. This is the alternative way of running this hypothesis test. Once you've got that critical value just there, you can check whether your test statistic goes beyond that, in other words, minus 2, minus 3, and so on, or whether it doesn't quite reach it. If it doesn't quite reach it, if it gets to about there, then it means it's still within the acceptance region, so therefore you would not have enough evidence to suggest the manufacturer's claim is incorrect. If it goes past this point though, and it ends up being down here at minus 1.5, then you can doubt the claim. So you can compare the z-score and the test statistic, including the hypothesis test. If the test statistic is negative, then you're looking at it being down there. And if it's positive, or if it's greater than that, then you would accept it. Okay? But that's only if the test statistic is negative. Then below it, you'd reject, and if it's greater than you'd accept. If on the other hand, it's the other way around, so in this case, it's going to be a greater than 0.1, so this is a 1% significance level, then you notice that you're getting this value just here. So you can grab your calculators, 2.33, that is our test statistic. What can we say about 2.33? Well, because it's positive, okay, because it's positive, if you get bigger than 2.33, then you fall into the critical region and therefore you'd reject the claim. If on the other hand it didn't quite meet it, maybe it only got to 2 or 1, then you'd accept the claim. Don't have to, it's not enough evidence to suggest it's incorrect because it didn't pass that finish line. Okay, so we're going to just recap on that previous question and just look at the difference between using that alternative method. Most of it's the same though. So the still answer, you'll still define the population parameter. So that bit's the same. You still write the null and alternative hypothesis and the significance level. That part's the same. So still the same parts as before. State the population distribution and calculate the sample mean. Same as before, no difference. So we've got that. We've got 1003. We got the test statistic and we know it still comes out to be 2.078. It's this part here that we don't do any work with. That is our test statistic. We need to know whether 2.078 goes beyond the critical value or it's before the critical value. Because if the critical value was, let's say, 2.1, that's just on that side, so therefore you would stick with the original claim. If the 2.07 passed the critical line, then you would be able to say, oh look, we've got enough evidence to suggest that the manufacturer's claim is incorrect. Okay, so let's keep that 2.07. Let's calculate the z-score for this test statistic. So in this case, it was a 5% level, but it was a not equal to. So we're looking for, and we've noticed because it's positive, it's over here, we're looking for that critical value just there. what is that critical value. So you grab your calculators, work out the probability it's going to be greater than whatever number is equal to 0.025, and your calculator will tell you 1.69. Sorry, 1.96. Now then, once we've got 1.96, then we can check whether this passed it, and therefore it's in the critical region, or is it before it, therefore it's in the acceptance region. And you can clearly see now why this method might be a bit nicer for some people, because it's a lot easier to check a test statistic against this critical value. I can clearly see that 2.07 is here within the critical region, so therefore we would reject the claim that 1000 is still right. Okay, so compare it, write your conclusion. 2.07078 is greater than 1.96. It lies in the critical region. So there's excuse me, tongue-tied. So there is sufficient evidence to suggest that the mean volume of juice differs from the 1000 millimeters it was originally. Right, it's worth making sure that you practice some of those. In fact, practice quite a lot of them. We will be putting some of them in your homework packs as well to keep practicing them. But good luck.